I just want to give you a minute to take a look at the answers that I've written up here so you can compare the results you had for the two practice problems using the direct comparison test. So I haven't included all of the details, but I want to talk through what the calculations are that you should show every time you use the direct comparison test here. So the first thing you need is a conjecture, whether you're going to show that your series diverges or converges. So in this first instance, we have that the series should diverge. So if we want to show divergence, we need to select an appropriate comparison series, and so in particular, the comparison series has to have two properties. The first thing is that it needs to diverge. Okay, and so if we compare with the harmonic series, we can see that that series diverges. And the second thing that we need is we need all of the terms, or at least all of the terms, sufficiently far out. So we may be able to ignore, say, the first term, but at least after some point, all of the terms. Whoops. I was trying to highlight here. After some point, all of the terms must be must satisfy this inequality that I've highlighted here. In particular, we have our divergent comparison series whose terms are 1 over k, and term by term, the terms of our series all have to be greater than that divergent series. And so once we have those two things, then the direct comparison test tells us that our series also diverges. Okay, in the second example, we want to show convergence, and so here, notice that we need to find a convergent comparison series, and so I've selected 1 over k squared, and that converges. And then we need to show, the second thing we need to show is that term by term, the terms of 1 over k squared have the right relationship. And so to show convergence, we need the terms of the comparison series to always be greater than the terms of the series that we are investigating. And so here in this case, it's true that for all k, 1 over k squared is greater than 1 over cosine k plus k cubed. Now, the reason I elected to use 1 over k squared and not 1 over k cubed is because cosine of k can be as small as -1. And so I just didn't want to have the possibility of a negative value of cosine of k making this inequality not hold. And so if I switch to 1 over k squared, then because the k cubed in our series is so much larger than k squared, that takes care of that problem. Okay, so, but you would want to carefully write that down if you were working this problem for a homework assignment or another application. Okay, so we're going to move on now. So you notice that there's a lot of things we had to show here. We had to first guess convergence or divergence, and then we had to find the comparison series. And the comparison series we found, we had to have a very specific relationship between the terms. So the next test is also a comparison test, but it's slightly simpler to use in many cases because you don't have to have a very rigid term-by-term relationship. So we still are going to need a comparison series, and we will still need to find the appropriate comparison series depending whether we're guessing divergence or convergence. But in principle, there's fewer things to check here. So the comparison test for series is found in section 8.3.4 of your text, so that you can find that easily. Okay, And so I've put a statement here for you. This is just straight from your book, so just for convenience for your notes. So the idea is if we have two series with positive terms, and we look at the ratio, term by term, of those summands, then if that ratio, the limit of those ratios as k goes to infinity is a constant, then the series have the same convergence behavior. So either they both converge or they both diverge. And I'll just say a word or two about why that is. So roughly speaking, what we're saying is that if the limit as k goes to infinity of bk over ak is equal to c, then what we have is that the terms of the series bk, so the terms bk behave similar to the terms, c times ak. And of course, a constant times series terms won't change the convergence or divergence of the series that we're interested in. So let me write it this way. So the sum of BK's converges if and only if the sum of the C times AK's converges. Right? And similarly, right, this is just, it's the same statement, but I'm going to write it out here anyways, just to be really complete. So the sum of the BK's diverges if and only if the sum of CK times AK, oops, I'm sorry, CK, it's just one constant C, so there is no CK. So this is C times the sum of the AKs. Okay, and so if this series diverges. Okay, so this is kind of a rationale for the limit comparison test. I'd like to go through just a couple of examples of this, and then I want to give you a quick extra way we can squeeze some extra mileage out of this theorem sometimes. So the first example that I'll talk about is this first one, k squared plus 6 over k to the fourth minus 2k plus 3. Those are the terms that we're adding up. And so what we might think about is what kind of behavior this is exhibiting. And what we see is it's a ratio of two polynomials, and the leading terms here are k squared and k to the fourth. So what we believe is that this series should behave like, so let me just kind of make some notes for us off to the side. So this series should behave like the series that we would get by dividing k squared over k to the fourth, in the sense that as k gets large, the terms of our series kind of look like the terms of k squared over k to the fourth, right? Which if I simplify, that's just the sum of 1 over k squared, right? So, so that's our comparison series. Now, if we were using direct comparison, we would need to double check that everywhere our series, this larger rational function here, is strictly less than for every term, at least every term after some point, satisfies the inequality that these terms here are always, these terms here that I've just underlined are always less than or equal to 1 over k squared. And that's an extra computation that if we use the limit comparison test won't be necessary. So I'm going to go ahead and write out the limit that we need to compute. So what we'll notice is, well, what we'll need to check is the limit as k goes to infinity of, and now we can put either series in the numerator or denominator, it doesn't matter. So, so we'll just go ahead and use our series in the numerator. So we'll have k squared plus 6 over k to the fourth minus 2k plus 3. Okay, so this is our series, and then we need to divide by 1 over k squared. So this is the limit that we need to take. Okay, and then this is going to be equal to the limit as k goes to infinity, and now I'm going to just go ahead and multiply by the reciprocal of the bottom fraction here just to simplify my fractions a little bit, and we'll have k to the fourth plus 6k squared over k to the fourth minus 2k plus 3. And you can see then that this limit is 1. And so therefore, since the sum of 1 over k squared converges by the limit comparison test, the sum k squared plus 6 over k to the fourth minus 2k plus 3 also converges. Okay. So let me do a second example for us here. And so here we might wonder kind of what's happening if I start summing up sine of 1 over k, or, well, I mean, that's what we've been given here. And so I want to use an approximation here. So as k goes to infinity, so again, what we're looking at is end behavior. For k large, what we should notice is that 1 over k is approximately 0. Okay, so is small, and so in fact we'll use the approximation that that sine of x is approximately equal to x for x near 0. Okay, and one way to think about that is if you think about derivatives, right? The tangent line approximation to the sine curve is exactly the line y of x equals x near 0. So we want to kind of be thinking about this this representation here, in fact, what this tells us then is that sine of 1 over k looks like 1 over k for large K. Right, so this is kind of telling us that we we may want to be using the series 1 over K for our comparison. So let's do that. I'm going to go ahead and erase this little diagram here so I have a little more space. And then let's compute. So the limit as k goes to infinity of, okay, and now we'll do sine 1 over k over 1 over k here. And this is just equal to 1 by exactly this observation that we made here. Okay, and therefore, since the sum of 1 over k diverges, then by the limit comparison test, so does the sum of sine 1 over k. All right, so so I had mentioned that there are a couple of extra bits that we can squeeze out of the limit comparison test. So suppose that we have, for example, the series. Let's say example. Suppose that we have the series 1 over x squared ln of x, and we choose as our comparison. And so here's so the extra bits we can squeeze out are if we happen to choose a less efficient comparison series. So suppose that we choose suppose that we choose for comparison, if we choose for limit comparison the series 1 over, whose terms are 1 over, oh goodness, okay, I'm using x squared here, and I want to use k really. Okay, so 1 over k squared ln of k. So suppose that we use the series 1 over k squared. Well, let's look at this. So if we look at the limit as k goes to infinity of 1 over k squared ln k over 1 over k squared, right? This is equal to the limit as k goes to infinity of k squared over k squared ln k. And this limit is 0. So under normal circumstances, under the strict definition of the limit comparison test, we do not get to make any conclusion. So these series need not have the same convergence properties. However, if the series in the denominator converges, then the series whose terms are given in the numerator here must also converge. Because what is this limit statement saying? If this limit is 0, well, then let me go ahead and switch colors here. Then the statement that the limit is 0 means that the terms of the series 1 over k squared ln k, right, this was the ones in the numerator, decrease faster than the terms of 1 over k squared. And since this series converges, since 1 over k squared converges, then our series must also. So our extra statement that we can add here is if the limit as k goes to infinity of bk over ak equals 0 and ak converges, some of the ak's converges, just clean this up a little bit here, then the sum of the bk's also converges. Okay, similarly, if the limit as k goes to infinity of bk over ak is equal to infinity and the sum of the ak's diverges, then the sum of the bk's also diverges. Okay, and why is that? Well, that's because for a similar reason, right? If this limit is actually infinity, then that means that the terms of the series sum of the bk's, those terms are increasing faster than the terms of the sum of the ak's, and that series is already diverging. So we can then conclude that the sum of the bk's is also divergent. So I just wanted to kind of give you that as, you can squeeze a little extra information out. In general, though, we don't get to conclude anything unless you're in one of these specific cases about a 0 or an infinite limit. Okay, so we're going to go ahead and stop here, and I will give you the two, I guess there's just one your turn question here to determine whether this converges or not and use limit comparison to analyze it. And we will pick up with the next video.